Welcome to this explainer. Look, advanced trig can feel like a bit of a maze, right? But today, we're taking all those complex formulas and streamlining them into your own personal mathematical toolkit. We're going to upgrade your problem-solving capabilities, look at some fascinating graphs, and equip you with the exact strategies you need to completely master this subject.
So let's kick things off with the big question. What actually happens when the comfort of a perfect 90-degree angle just disappears? I mean, up until now, basic sine, cosine, and tangent have been your absolute best friends. But they totally rely on that one perfect corner. The second a triangle leans, stretches, or flattens out, those standard tools, they completely break down. We're going to need something a lot stronger.
To get us there, here's our roadmap for today. We'll start by moving beyond right-angled triangles, then master the core trigonometric rules. After that, we'll unlock the power of radians, visualize trigonometric graphs, and finally wrap up with some crucial identities and exam secrets.
All right, let's jump right into part 1, Beyond Right-Angled Triangles, our new reality. You see, while basic triangles yield to those simple, familiar tools we all know, non-right-angled triangles are a whole different beast. They require some heavy-duty machinery, specifically the sine and cosine rules. We are officially stepping into territory that demands a completely new strategic approach.
Which brings us perfectly to part 2, mastering the trigonometric rules. These are basically your core weapons. Now, the absolute key here is knowing exactly when to deploy which formula. You want to save precious time and cognitive load, right? So here is your golden rule of thumb. Burn this into your brain. CSAS, use cosine. CAAS, use sine. That's side angle side for cosine and angle angle side for sine. Memorize that divide and you're golden. Let's break that down a bit more strategically. You're going to use the sine rule when you know two angles and one side, or two sides and an opposite angle. But, and this is a big but, you must switch over to the cosine rule when you're dealing with an included angle. You know, that classic side angle side scenario. Oh, and also if you just happen to have all three sides, cosine rule all the way for that one. What's really cool is how efficiently the sine rule finds a missing side. It's literally just 3 simple steps. First, identify your knowns. Second, set up a simple cross-multiplying proportion with your corresponding sides and angles. And third, just isolate the unknown. Bam! It is a super fast, incredibly direct calculation. Now, the cosine rule follows a similarly predictable rhythm for those side angle side scenarios. You just plug your adjacent sides and that included angle directly into the formula. But listen closely, because here is the most important step. Do not forget to take the square root at the very end. Seriously, actually, scratch that. It's the only place people usually mess this up. Remember the square root. Before we totally leave triangles behind, we've got to rethink area. You can basically forget half base times height for a minute. In advanced trig, area is 1/2 a times b times the sine of angle C. The vital catch, the absolute deal breaker, you must use the included angle for this to work. It has to be the angle sandwiched right between your two known sides. Okay, moving on to part 3, the power of radians, giving us a totally new perspective. So what is a radian? Basically, a radian isolates the true relationship between a circle's radius and its arc. It totally frees us from that completely arbitrary 360-degree system we're so used to. To make the jump from degrees into this much more natural mathematical language, all you do is multiply your degrees by pi and divide by 180. Converting your mindset really just requires memorizing a few key milestones. For instance, half a circle isn't just 180 degrees anymore, it's exactly pi radians. 90 degrees? That's pi over 2. A full circle is 2 pi. Committing these specific benchmarks to memory will drastically speed up your problem solving. It's kind of like learning the local currency before a big trip. And once you're working in radians, calculating slices of a circle becomes unbelievably streamlined. Just look at how clean these equations are compared to the degree versions. Arc length is literally just the radius times theta. Sector area, just 1/2 the radius squared times theta. So elegant, right? But, and I cannot stress this enough, if you plug degrees into these formulas, your answer will be wildly, comically incorrect. Theta has to be in radians. Let's shift gears to part 4, visualizing trigonometric graphs. Welcome to the world of waves and asymptotes. Taking things off the triangle and onto the Cartesian plane reveals the continuous, flowing, wave-like nature of sine and cosine. Honestly, they are basically identical twins. They both bounce between -1 and +1, and they both complete a full cycle every 2 pi radians. The only real difference is their starting block. At x equals 0, the sine wave starts at 0, while the cosine wave starts right at its peak of 1.
Then we have the tangent graph, which just completely breaks the mold. It repeats twice as fast, and it literally fractures at specific angles where it becomes mathematically undefined. Why? Well, because tangent is sine divided by cosine. So whenever cosine hits 0, like at 90 degrees or 270 degrees, the graph shoots off into infinity. That creates these invisible vertical barriers called asymptotes. Plus, its period is only 180 degrees, totally unlike sine and cosine.
Now, what happens when you need to morph these waves? Well, every single letter in the transformation equation acts as a specific lever. The A dictates your amplitude, basically how tall the wave gets. The B compresses or stretches the period. C slides the entire wave horizontally left or right, and D shifts the whole shebang vertically, up or down. Once you understand this anatomy, you can interpret literally any transformed graph thrown your way.
Finally, let's open up Part 5, Identities and Exam Secrets. Think of this as your cheat code kit. These equivalent forms are exactly that, your mathematical cheat codes. They let you swap out complex, messy terms for much simpler ones during algebraic proofs. The Pythagorean identity, sine squared plus cosine squared equals 1, is an absolute lifesaver, and you can easily rearrange it to isolate either sine or cosine. Then there's the tangent identity, your golden ticket for breaking tangent right back down into sine and cosine. These pop up on tests constantly, so they really need to be second nature. Okay, pause. Before you do absolutely anything in an exam, check your calculator mode. Seriously, being in the wrong mode is the #1 destroyer of good grades. No joke. If a question is in degrees and you're chilling in radian mode or vice versa, literally every single calculation you do will be completely wrong. Always double check that tiny little indicator on your screen before you start punching in numbers. In fact, actively scanning for common traps is your personalized survival guide. Let's quickly recap them. Don't mix up your sine and cosine rules. Never forget that arc length formulas absolutely demand radians. Always make sure to use the included angle for triangle area, and when transforming graphs, remember to correctly divide by that b-value to find your brand new period. Combine those hazard checks with these quick tips, and you are going to approach any advanced trig problem with absolute confidence. Always write down your units in geometry answers. Know your common radian values by heart. Practice sketching those wave graphs freehand until you can do it with your eyes closed, and lock down those basic identities. Do all that, and you are totally set for top marks. So, as we wrap up this explainer, I want you to look around and ask yourself, where else are these invisible trigonometric patterns shaping our physical world? From the repeating crests of the ocean tides to the acoustic waves that make up your favorite song, these formulas aren't just ink on a page. They are quite literally the underlying code of the universe. Keep looking for them, and keep learning.